All right, double displacement. A reaction in which aqueous ionic compounds rearrange cations and anions, resulting in the formation of new compounds. General equation, you see there, A, B, C, D. We swap A with C because the metal swaps with the metal. So we get AD and then CB. Again, this is very much review. Grade 10, you would have, learned about trading partners. Like, for the single displacement, your teacher might have talked about someone cutting in a dance, right? Here we've got everybody trading partners. What do they call that kind of a dance? Back when I was in elementary school, they called that a snowball dance, I think. Okay, everybody, snowball. We don't want anybody feeling left out. Grade 8, dance in the classroom, because that's what you do. Can we have a dance? Bring all of our records. Yes, records. Olivia Newton-John. Somebody tried to play Let's Get Physical, Olivia Newton-John. You know what I'm talking about? I went to a Catholic school. Ooh. Big trouble. So that finished very quickly. Anyway, all right. So as not to disappoint anybody, snowball. Still doesn't matter. Still get disappointed. Anyway. I'm sure your teacher might have used such an example last year to describe such a thing, right? Trade partners. Oh, that's nice. So then what do? You get a double displacement reaction. You trade the partners and you get full marks, right? Very easy. You guys probably think that was the easiest reaction ever. Again, just like with single displacement, on Friday I introduced to you the fact that some single displacement reactions are failures. They don't result in a chemical reaction. And that's going to be the same here with double displacement reaction. So what we want to teach you today that is new is how to identify a successful double displacement reaction. Something that shows us something interesting, right? Because a failed chemical reaction isn't interesting. You can do a single displacement reaction that doesn't actually take place. You can trade them out. But if it doesn't give you evidence of a chemical reaction, it isn't, right? It isn't a chemical reaction. Now, I haven't gone over evidence for chemical reactions. That's that note that I'm leaving to the end. But you guys all know what the evidence is for chemical reactions. Quick review here. How do I know that a chemical reaction has taken place? What do you see when a chemical reaction happens that indicates to you, we have a reaction? You go over this in grade 9, you go over in grade 10, give me one of them. There's a color change. What else? Yep. A new solid is formed, precipitate. Yep. Gas is formed. Excellent. Now we're rolling. Yep. Heat or light is produced. Is that everything? Have we got them all? Am I missing one? I thought there was 5. An odor is produced. Do some teachers put an odor? Could be. There can be gaseous products produced that produce a new odor. I would accept that. That's good logic. Anyway, it doesn't matter. We all know that, right? That's what makes chemistry interesting, because you do something, you mix things, and something almost magical happens, like something new is produced, right? And that's what makes a successful reaction. That's what indicates to us a reaction has happened. And just like in single displacement reactions, you can, just for double displacement, just like in single displacement reactions, you can have a situation where you add 2 compounds together that are dissolved, you put them together and nothing. No reaction. Not a successful reaction. Again, you can trade the partners around, but if something interesting doesn't happen, it's not a successful double displacement reaction. So that's what we want to talk about today. How do you determine a successful double displacement reaction? And there are essentially 3 types of double displacement reactions that we have to look at in order to analyze this. So the first one is precipitation reactions. A double displacement that forms a precipitate. Now, at the very end of that statement, that forms a precipitate, a solid that has a low solubility in water. We have to talk about what we mean by solubility. Does anybody know what solubility means when it comes to a substance? Yep.
How well it dissolves.
How well it dissolves. Perfect. Some substances dissolve very well, and some ionic substances, or even, doesn't even have to be ionic, could be molecular, but we're talking primarily here ionic. Some substances don't dissolve very well at all. It has everything to do with how sticky the ions are. If the ions are really not very sticky and they're not being held together very strongly in the crystal lattice, you put it in the water, those forces aren't strong enough, the water pulls them apart, and we have successful dissolving. But some things, especially things that have big charges, like +2 and +3, as opposed to just +1 and -1. So things that have big charges in their crystal lattice are stuck together quite strongly, and therefore they don't dissolve very well. An example of something that dissolves easily, well, you tell me. You guys have dissolved substances before, especially when you're cooking. You use substances, you dissolve them all the time. Tell me a substance that dissolves quite easily. Yep. Yeah, sodium chloride. Sodium chloride is very soluble. You can put a lot of salt in water before you get to the point where it can't dissolve any more salt. You can really dissolve a lot of it. We would say that it's highly soluble. Calcium carbonate, which is what chalk is. And calcium carbonate is essentially what's found in marble. All right, so if you've got a marble countertop at your house, it's made up of primarily calcium carbonate. The difference between your marble countertop and this chalk is that the marble or the calcium carbonate in this chalk has been ground down into a fine powder, and then it gets into a forming device where they squeeze it back together and it holds just together just enough so that when you drag it across the chalkboard, some of that powder comes off. If I were to take a chunk of marble, like a chunk of a countertop, it would be made of the same substance, but if I dragged it across my chalkboard, I'd take a big chunk out of the chalkboard because it's made up of a big crystal. This is made up of tiny little pieces of powder that have been squeezed together, kind of like a pill, right? A pill is made up of powdered medical, the medical ingredient along with some fillers so that it can be the size that you can actually handle it. And then it's squeezed together in a pill-making machine so that it holds together by the pressure. Same thing with this. But if I were to put the chalk in the water, it's going to sit there. It doesn't matter how much I stir it up. Even if I were to break it into little chunks, I would still end up just with some powder sitting at the bottom because calcium carbonate is not very soluble. It doesn't dissolve. All right? Now, you can introduce the ions of an insoluble substance into the water in a different way than just dumping the substance into it. Now, that's quite a statement there. I'll say it again. You can introduce the ions. Let's say I'm talking calcium and carbonate. Right now, the calcium and carbonate that is in that water sitting there was already stuck together as calcium carbonate. But what if I could take a solution that contains just the calcium and the solution that contains the carbonate separate, and then I bring it together into the same beaker? Then what I've done is I've introduced the calcium and the carbonate into the beakers from a different technique, right? So what I did here in this one, dump it in, calcium carbonate, CO3, it's already in there, and it's a solid, it doesn't dissolve. But I could also take a solution that contains the calcium ions, +2, and take a solution that contains the carbonate ions, -3, and I could pour them together into the same beaker. And now what happens is, I've got the calcium ions in here, and I've got the carbonate ions in here, and in the end, they still don't want to be soluble. They still don't want to be in the dissolved form. So what do? They stick together. They're sticky. So they'll stick together, and they'll quickly form some calcium carbonate, solid, which will settle down to the bottom. And what do we call that when that solid settles down to the bottom? What do we call that term? It precipitates. So what can happen in a double displacement reaction is, you can take two things that are soluble in one solution, but when you bring them together, if they're not soluble, then they'll stick together and they'll form that solid and they'll settle down into the bottom. So our job in the double displacement reaction is to determine what will be soluble or not. Will calcium carbonate form a solid, or will it stay aqueous? And we do that with a data table. Just like we've been doing with the activity series, we have a data table that determines the solubility of various substances. So you can write down solubility rules, and you can then go to your data sheet and you can track down the solubility table. And on this solubility table, you take your positive ion that you're wanting to analyze, you take the negative ion that you want to analyze, you meet them across until they meet, and what they've done in a very handy way simply told you, is it solid or is it aqueous? Now we've made this almost too easy, but I don't think it's something that's worth, getting too excited about. But if you check out calcium and you check out carbonate, what's it say when you get to the calcium and carbonate when you put them together? Yep. It says S. It's going to become a solid that is going to precipitate out. Very straightforward. If it says AQ, it means it doesn't form a precipitate. Now, I just finished my lesson today with the grade 12s that shows mathematically how you can predict that. In the grade 12 course, I will be giving you a big table of numbers and all kinds of exciting calculations, and we will mathematically determine whether it forms a precipitate. Right now, we're just kind of starting into it, and I'm just introducing you to the fact that it could be a solid, and this is how we determine. In previous years, we've used a table, and I'm trying to find an example of it. I had one here, and I'm not going to, whoop, nope, that's not the one. Oh yeah, this guy. In previous years, we used the table. Instead of it just telling you whether it's a solid or aqueous, it used terms like not soluble or insoluble, and slightly soluble, and soluble. And then you'd have to convert that over to an AQ, right? If something's soluble, it's going to dissolve, and then it's aqueous. If something's insoluble, it doesn't dissolve, and it forms a solid. So you had to do a little extra step a few years back. But then we went away from this periodic table. I made a new data table, and you don't have to think and worry about that stuff. So I've made it very simple for you, all right? All you have to do is take a look. Now, when I was in high school, we used a table like this. But then my chemistry teacher, he said, you guys got it easy. They used to have them memorize the solubility rules. There are a series of rules that you can memorize and follow to determine what ion is going to do what with others. Now, I don't have you memorize it, maybe I should, but he would sing the solubility song. Let me show you the solubility song. It's kind of funny. So if I go to course content, and I put it in here, if you guys want to sing the solubility song for yourself, you can go online, you can download it. All right, so if I go to part 3 here, part 3, and I go to, did I put it in notes or handouts? Nope, put it in handouts. Notes, handouts. Oh, the solubility rules song. Here we go. Let's open it up. So as you can see here, solubility rules song, sung to the tune of 99 bottles of beer.
Really?
Yep. Now, I'm not going to sing it, but, because I'm not going to sing. No, I don't, a video of me singing it, that would be entertaining. But I do like it. It does kind of do things. Potassium, sodium, ammonium salts, whatever they may be, can always be dependent on for solubility. It's not. If it's soluble, if anything that has potassium, sodium, or ammonium in it, it'll always be soluble. So what letters would it be on your table if it dissolves? It's going to be aqueous. Take a look at sodium on your table, all the way across sodium. Yeah, see, AQ, it's all AQ. And you'll find for potassium, that's the same, and you'll find for ammonium. Now, I'm not going to have you memorize the whole table, but you know what? In a lot of our reactions, I use sodium and potassium and ammonium. And if you can remember that potassium, sodium, ammonium salts, whatever they may be, can always be dependent on for solubility, then you don't have to check the table every time, and it saves you a little bit of time, and then you don't panic at the end of tests because you've saved some time. So I would say that the first verse here does have a function. So anyway, I like it. When asked about the nitrates, the answer is always clear. They each and all are soluble is all we want to hear. That's a good one as well. Nitrate is a negative ion. Take a look at nitrate all the way across the line. What is it? Or down, all the way down. All aqueous. All aqueous. Now think about that. If I ask you a question, propose 2 reactants that you could mix together that are aqueous that would produce a precipitate of calcium carbonate. Well, what that means is we want calcium to be in a solution and not precipitated. What ion are you going to stick it with? Calcium's positive. I need to stick it with a negative ion, and I need it to be aqueous. Yep. Nitrate. Because nitrate's aqueous with everything. We have all kinds of nitrates in our chemical storage room because when I set up a double displacement reaction and I want everything to start out aqueous, I'm picking the nitrate because it's going to be aqueous. And that's a good thing to know, a good thing to think of. If I need to get the carbonate into the water, look at I said -1, that's supposed to be -2. If I put the carbonate and I need it into the water and I need it to be aqueous, what should I put, what kind of chemical should I grab off of the shelf in order to make that? I want an aqueous version of carbonate. I need it stuck to something that is positive that will be aqueous for sure. What should I pick? Potassium, sodium, ammonium salts, whatever they may be, can always be dependent on for solubility. What should I pick? Yep. Potassium. I don't want potassium nitrate. That's going to be really soluble. Oh, potassium carbonate. So if I were to put potassium carbonate with calcium, what was the other one again? Nitrate, they're both going to be aqueous, but when I mix it, the calcium and the carbonate will get together, and I will have a precipitate form. All right? So yes, the The solubility song is a little silly, but I do like the first two because it tells me what I can use if I need something soluble. And then most every chloride soluble, at least we've always read, saves silver, mercury, and slightly the chloride of lead. What that essentially says is pretty well all chlorides are soluble. Save means except silver, mercury, low oxidation state mercury, and lead. Anyway, you guys are going to be using the table, but keep in mind, potassium, sodium, ammonium, salt. I'm not going to do it again. You get the idea. Okay, so let's not write anything down here, folks. I'm getting you to check the chart. I'm getting you to tell me whether we're going to put an S behind this thing or whether we're going to put an AQ behind this thing. Copper 2, it looks like it's a copper 2. Carbonate, what am I putting there? Is it a solid? So that's going to be a solid. Potassium nitrate, don't look at the chart. It's soluble. So what does it get behind it in the equation? Aqueous. See? That's so much quicker than actually looking at the chart. That's like super aqueous. Aqueous and aqueous all the time. Lead. Which version of lead is this? Lead 2 and iodide. What is it? Lead 2 iodide? Solid. That's going to get a solid. So if I were to get lead 2 ions in the solution and iodide ions in the solution, that's going to form a precipitate. Copper 2 iodide. What do we got? Ray, did you see it there? Can't find it? What do we got? Does it say no reaction or does it say decomposes? Sends blank? All right. And that's good. That's fine. Some of them will break down into other products. I'm not sure what this one will do. Sometimes they're not isolatable. And that means a secondary reaction happens. And that secondary reaction likely happens with water itself. So when these chemicals get together, either the copper or the iodide will do a reaction with an H2O molecule and turn it into something else. It won't allow it. It probably goes into I2. The copper probably stays in the solution. The I2 probably becomes iodine, probably turns the solution purple, and then the water likely becomes a hydroxide or something, or maybe even some hydrogen gas form. So there's some secondary reactions that happen there, so we don't deal with those. Okay. So let's do some double displacement examples here. Just put EG. Don't write all of this stuff. I'm going to explain to you what we do when we do a double displacement reaction and how we do it properly. Just put EG. And here's what we do. You're going to complete and balance. That's good old grade 10. Swap partners. Come up with the proper formulas using the crossover. Balance it up. But the second part of a double displacement reaction is to check and include the subscripts and do it for all of them, all of the reactants and all of the products. And so you're using your chart and you're simply putting S or AQ. And that will indicate whether we will have a successful reaction or not. No need to write down all these instructions. I'm going to do the examples. You'll get the idea. So, magnesium is going to go with chloride, and then I've got to cross over to make sure that I have the right formula. So I write down Mg, I write down Cl, I check the oxidation state of magnesium, it's in group 2, chlorine is -1, I cross it over, and notice it looks like they truly swapped positions. But the only reason it looks that way is because calcium is also +2. So it ended up being the same crossover. But you have to check each time. Calcium sulfate, CaSO4. There you go, buddy. Now check. What am I putting for magnesium sulfate? Somebody check. Now you're looking at your chart. S or AQ. I want them for every one. Atlee? AQ, that's good, because I want it to be in solution to begin with. Next one. Yep, Atlee. AQ again. Good. Keep going, Atlee. You're on fire here. AQ again. And solid. This is a successful double displacement reaction. We will see a precipitate form. Okay? Whether it settles out nicely, sometimes it forms this goopy, gelatinous mess, but you'll see something. Okay? You could get something where they're all AQ all the way across. What are you going to see if that's the case? Yeah, nothing. It may be colored. They could have color, but you won't see anything precipitate out. It would just be a mixture of the, if they were both colored, it'd be literally a mixture of the colors, like if you added meal with water. Yeah, that's exactly right. That's what I was thinking about. Now I'm thinking about that silly commercial. The playoff beard squirt. My wife hates that one. I find it a little enjoyable. So, don't wait for me at this point. If you got a handle on it, get the pencil out, right? If you're unsure, swap the partners, do the crossover, balance it up, then check for solid and AQ. What do I need to balance this one up? Yep, Dallas. 2 on the KCl. Notice my potassium, what am I putting there? Don't make me sing it. Don't make me do it. Aqueous. And therefore, automatically, what else can you do? Yep. KCl. It's a little silly, but it'll save you a little bit of time when you spot those ones that are all aqueous. Yeah, that's good. That's good. Oh, I thought he is serious. What part of the don't make me sing it did you not understand, man? Jeez. Killing me. Barium chloride. Aqueous. That was the third verse, by the way. We don't want to worry about the third verse. Barium sulfate. Yep. Solid. Successful double displacement. Look at even just looking at the first 2. What can I do with those? All of them aqueous. The nitrate and the potassium. Again, make sure you trade them and you cross over to get the formulas. What do I need to do with that one to balance it up? Yep, Chelsea. 2. 2. And we already said this is aqueous. This is aqueous. Look at this one. Definitely aqueous. And I think we looked at a PBI2 on the previous slide. Didn't write it down, but what's that one? That's solid. Okay? Yes, you can have it where they're both solids. You'd get a mixture of solids in that thing, but you could have it that they're both solids. That's a possibility. Okay? Questions, concerns on how to determine whether a precipitate forms? Pretty straightforward. Okay. Let's now talk about neutralization reactions. Now, neutralization reactions, when they take place, Nothing visual is really exciting about it. It really is two aqueous, usually transparent and usually colorless liquids that come together and produce transparent, colorless, solutions at the end. You can have a precipitate formed in an in a neutralization reaction. It is possible. But sometimes you don't see anything exciting taking place. You might think that that's a failed reaction, but we are getting a new liquid formed. That new liquid is water, right? Water I'm missing an and in there, aren't I? I'm right in here. Double displacement reaction occurs in which water and an ionic compound called a salt are produced. So this is really like the formation of a liquid, a new liquid. Sometimes cannot be detected. You could detect it with an indicator. If you had an indicator in there like phenolphthalein, it could go from being pink and purple if it was a base, and then as it's neutralized, it would become clear. So you would see the neutralization taking place. Let's do some examples. Again, just write EG. Oops, I'll bring them all up. And if you want to do them and then go ahead, then that's great. Now, we haven't talked about predicting the products of a neutralization, but we now have the tools to do it. You need to realize that a neutralization is a double displacement. And so, where's the H going to go? Where's the H going to go? What's it going to go with? Yep, Brendan? With the hydroxide. And remember when we were talking single displacement the last day, you can think of water as being hydrogen hydroxide, right? That's how you're going to get that single displacement reaction correct that I warned you about. So you're going to end up with water, a hydrogen hydroxide, an H2O. What physical state is H2O in? Yeah, Atlee? It's a liquid. Now, you're not going to find it on your solubility chart, but it is a liquid. So we start with aqueous hydrogen and aqueous hydroxide, and it makes a new liquid. So that's what makes this kind of special. And what's the other product here? Yep, Janessa? NaCl. And in this case, it technically is what we call salt, but it doesn't have to be. You'll find in the rest of them, we will have other salts. And technically, any ionic compound is considered a salt, right? That's the general term for an ionic compound. In this case, we have actual table salt being formed. You should check your solubility tables for these as well. They could be a solid, but notice we've got sodium here, so it is aqueous. Now again, we should balance. I've already told you how to balance the neutralization reactions. Do the hydrogens and hydroxides last, and remember that one hydrogen plus one hydroxide equals how many waters? One water. So sodiums are good, chlorides are good, so we don't need any numbers there, which means I have one hydrogen and one hydroxide. So how many waters? One. That is a balanced one. That's balanced already. It's a nice, easy one. Go ahead with the second, go ahead with the rest. Okay, for the first one, I'm going to get water again. H2O liquid. Magnesium with the bromide. MgBr. And what do I need for this? 2. So now to balance, I've got 2 Brs. So I need a 2 there. 2 hydrogens. 2 hydroxides. 2 waters. And magnesium bromide is? What state will it be in? Is it aqueous? Are there any magnesium ions that form a solid if you were to go down the magnesium line? What is it? Magnesium what would form one? Brody, what do you got? Magnesium carbonate forms a solid? What kind of acid would I need if I wanted to form magnesium carbonate solid as the other product? What acid would I have needed here? Yeah? I would have needed carbonic acid. Carbonic acid. That's kind of neat. That's a neat scenario. Yeah, yep. Well, we just had the discussion that if it was magnesium carbonate, right, that it would be a solid, right? So then the question becomes, what acid would I need? I now then have to bring my carbonate back over into this position, which means I need an acid that has carbonate in it. You see what I'm saying? See that logic? Okay. All right. This one, what are we going to get? I'm going to get my H2O liquid and lithium and sulfate. And what do I need to complete this formula? A 2 on the lithium, and therefore I believe I need a 2 over here. Is that correct? How many waters am I going to get? Yep, Brody. 2, good. 2 hydrogens, 2 hydroxides, 2 waters. Excellent. Does lithium form a solid with anything? Does it? What does lithium form a solid with? Sulfate? Phosphate? Phosphate? What acid would I need if I wanted to form a lithium phosphate? Yep. Hydrogen phosphate, also known as phosphoric acid. I could have used phosphoric acid if that was the case. All right. One last type. Reactions that produce gases. There are many double displacement reactions that produce gases, but I am only going to introduce you to 2 of them, and therefore on a test situation you will only see these 2 examples, all right? In some form. It might not be exactly the same as this, but it is these gases that they would be formed, all right? So some reactions produce gases. Let's just do the double displacement reaction, get the products, and then I'll tell you where the gases come from. Hydrochloric acid with sodium bicarbonate. Now I introduced the bicarbonate here because there are all kinds of different bicarbonates or bisulfates, and what I want to introduce you to here is how we deal with a bicarbonate. The H is going to come in and it's not going to displace the H. It's going to displace the sodium and join up with that other H to complete that molecule. So when I've got a bicarbonate, it is the metal that is going to be leaving, all right? And then we're going to complete the compound with H's, and the sodium's going to go into that spot. So what am I going to get as products? Yep, Brendan? NaCl, which by the way is what? What's its state going to be? Sorry? Solid? You're going to make me sing that song again? He's killing me. Aqueous. Sodium, potassium, ammonium, salts, whatever they may be, can always be dependent on for solubility. All right. They made me do it. He's just trying hard now. What do we have for, what's the other product? What's the other product? H2, H2CO3, all right? And what is that? What is H2CO3? Pause for it. Okay. It's carbonic acid, very nice. All acids in this case that we're dealing with are aqueous, so it is aqueous. It won't be found on your chart. And this is carbonic acid. Carbonic acid. When you get carbonic acid as a product, H2CO3, aqueous, it will decompose. And we've already seen this reaction. This is the reaction that takes place in pop. Carbonic acid is in pop. And when you open the pop bottle, this decomposes into, does anybody remember? Lots of bubbles. And so what do we get? What is in that compound when it decomposes? Atlee? No, you don't get oxygen gas. Oh, hydrogen gas? If you could get hydrogen gas out of your pop bottle, that would be the most exciting thing ever. I would be lighting them on fire left and right. That would be cool. It's incorrect, Atlee, but you made a nice mental picture for me for this morning. That's pretty fun. What do you got?
Water.
Yeah, very good. Water and CO2. H2O liquid and CO2 gas. It is carbon dioxide. So when you get carbonic acid as a product, you can insert an H2O and CO2 for every carbonic acid molecule. If this was a 2, you'd get 2 H2O and 2 CO2. So we can rewrite HCl plus NaHCO3 produces NaCl. And now I need you to think, when you get carbonic acid as a product, you can rewrite that as being H2O and CO2. And to add the states, aqueous, aqueous, aqueous. What goes with the water? Liquid. And the CO2? Gas. Right? Bubble, bubble, bubble. That is your sodium bicarbonate, your baking soda, and vinegar. That's your baking soda and vinegar reaction. If you've ever made the volcano for the science fair. And if you never have, just watch some Disney television show that has annoying preteen kids on it, like The Sweet Life, or, I don't know, Wizards of Waverly Place. And I guarantee it'll involve a science fair at some point in time, and I guarantee they'll make a volcano that does something horrifically wrong. I know I'm completely right. I know. It's cliche, but that's what they do. And if you were actually going to do such a thing, that's the reaction. It's an acid with the sodium bicarbonate, which produces the carbonic acid, which then bubbles away, and away you go. It doesn't even have to be hydrogen carbonate. I could add the chalk, calcium carbonate, to vinegar, and it would bubble. All right? It simply has to be an acid with a carbonate, and you will get that reaction. Okay? All right, let's look at this one here. What are the products going to be in this particular reaction? Still double displacement. Nothing new. Trading them out. What are we going to get? Now, keep in mind, folks, I don't know if this is messing. Oh, you know what? I have a mistake in this. No, I don't. It's not supposed to be a 4. That's a 4. I do that all the time. That's got to be a 4. Terrible. That's my most common error. All right, now what am I going to get as a product? Yep, Brody. NaCl, NaCl, NH4OH. Excellent. NaCl, we'll write down the states in a moment. Well, NaCl isn't going to break down into anything. It's this guy that's going to break down into something. All right? aqueous, and NH4OH aqueous can decompose into, and you know why I write down an NH3 over there? Because I'm thinking ahead to what it's going to break down into. That's my mistake. It breaks down into NH3 gas, which is ammonia, and it stinks. You'll have a chance probably to smell it in the experiment. We use some of this. And what is the other product? Water, H2O, and that is liquid. So again, if you get ammonium hydroxide as a product, it can break down into that. So again, a little rewrite, NH4Cl, and that's aqueous, by the way, because ammonium is in the first verse. We don't see it a lot, but it is, and I'm not going to sing it. NaOH aqueous, it's got the sodium in it, and NaCl aqueous, and now I can rewrite as NH3 gas plus H2O liquid, and I apologize for the squeezing in at the very end there. And those are the only two examples of gases that I'll make you be aware of that you have to watch for. It is not necessarily the same reactant, but what you're looking for is the ammonium hydroxide as the product, then it'll break down, and you're looking for the carbonic acid as the product, and it will break down, okay? There are others, but we're just going to introduce you to these two, just because of the timing. Don't need to throw them all at you. Okay, and that brings us to the end of this lesson, which means there is your homework.